All right, so probability rule number one is any probability is a number between 0 and 1. So if we're closer to 1, that means it's less likely to occur. And the closer the number is to 1, the more likely it is to occur. Keep in mind, probabilities can be expressed as fractions, decimals, and percentages. All right, probability rule number two says the sum of the probabilities of all possible outcomes must equal 1. So if we consider all possible outcomes in any situation, and we can consider those outcomes using like a tree diagram or something of that sort, the sum, if we added up all those probabilities, they should equal to 1. So for example, if the probability of picking a blue M&M is 0.2, a red 0.3, a yellow 0.1, an orange 0.1, and a brown 0.1, what's the probability of picking a green M&M? So we want to find the probability of picking a green M&M. Well, we know that the sum of all of those probabilities should be equal to 1. So I'm going to add together the probabilities. So 0.2 plus 0.3 plus 0.1 plus 0.1 plus 0.1. So that's 5, 6, 7, 8, which is 0.8. That means the probability of picking green is going to be 1 minus 0.8, which is 0.2. So all the probabilities for all the colors should add up to 1. Here's another example. It says find the probability that a randomly chosen American has type AB blood. So here's a probability of someone having type O blood, type A, type B, and then type AB. So again, these are all possible outcomes. These are the only types of blood that you can have. So that means to find type AB, we're going to add these all together and subtract it from 1. So we need to find the probability of type AB blood. So I'm going to do 0.45 plus 0.40 plus 0.11. So what is that? 0.8, 0.96. And then I'm going to do 1 minus 0.96. Which is going to be 0.04. So the probability of having type O blood is 0.04. All right, so rule number 3 is the complement rule. So the probability of A complement is equal to 1 minus the probability of A. So in words, we might say that the probability that A does not occur is 1 minus the probability that A does occur. So when we see the word not, that indicates we should be using the complement rule. Okay, or when we see this type of notation, A complement, we know we should be using the complement rule. So it says if PA is the probability of rolling a number less than 3 on a single die, what is the probability of A complement? So using our formula, 1 minus the probability of A. Probability of A is rolling a number less than 3 on a single die. So the probability of A less than 3 would be rolling a 1 or a 2. So that's 2 out of 6. So that means the probability of A complement, we're going to be 1 minus 2 out of 6. So since this is fractions, we can actually easily subtract this. We can turn 1 to 6 over 6, and we can subtract. 6 minus 2 is 4, and then the denominator stays the same. So the probability of A complement would be 4 out of 6. All right, the next example says, using the table above, find the probability that a randomly chosen American does not have type O blood. So again, we're using the complement rule. Not type O, which means we subtract from 1. So it's going to be 1 minus the probability that they do have type O blood. So it's just going to be 1 minus 0.45, which is going to be 0.55. Last one, find the probability of not drawing a face card when picking a single card out of a deck of cards. So that means we're finding the probability that we're doing not a face, which is going to be 1 minus the probability of choosing a face card. Well, there are 12 face cards out of 52 total cards. So it's just going to be 1 minus 12 out of 52. So again, we can do that same thing where we change this to 52 over 52 and subtract the numerator. So 52 minus 12 is going to be, what is that? That's going to be 40 out of 52. So I'm just going to leave it as a fraction. All right, so now with another definition. So when we describe two events as being disjoint or mutually exclusive, that means there are two events with no intersection or overlap. So if we look at some of this, the example directly to the right, it says, which of the following pairs of events are mutually exclusive or disjoint? So A says the numbers above 100 and the numbers less than negative 200. So in that case, we have to think, is there anything overlapping in A and B? Well, numbers above 100 and the numbers less than 200, those look to be mutually exclusive or disjoint. So we think it's A, but let's go through the other options. Even numbers and numbers greater than 10. Well, 10 is an even number, 12 is an even number, 14 is an even number, and those are all numbers that are greater than 10. So that means that there is overlap there, so that means those cannot be mutually exclusive or disjoint. Numbers less than 5 and all negative numbers. Well, numbers less than 5 could be negative, so that means those are overlapping. D is odd numbers and the number 5. Well, 5 is an odd number, so those are overlapping, so those can't be mutually exclusive. And then lastly, negative numbers and odd numbers. Well, you can have a negative number that is an odd number, so those are overlapping. So that's why A is the correct choice. Those are the only pairs of events that are mutually exclusive. Okay, so the reason that that particular rule is important is because we use that in the addition rule. So the addition rule states that the probability of event A or event B happening is the sum of their probabilities minus the overlap. So we need to be able to identify the overlap in order to find the addition rule. So in symbols, we would say the probability of A or B is the probability of A plus the probability of B minus probability of A and B. So this right here is going to be whatever the overlap is. So if two events are mutually exclusive or disjoint, that overlap would be 0. So really you would just be adding the probability of A plus the probability of B. So it says, let's look at the example directly to the right. It says a die is rolled. What is the probability that the number is even or less than 4? Okay, so we want to find the probability that it's even or less than 4. So using my probability rule, that's going to be the probability that it's even plus the probability that it's less than 4 minus the overlap. So let's think through. The numbers that are even are going to be 2, 4, and 6. Numbers that are less than 4 is going to be 1, 2, and 3. And then the overlap is what's in both groups. So the overlap is going to be 2. So in terms of finding those probabilities, if we're rolling a single die, the probability of rolling even would be 3 out of 6. Probability of rolling a number less than 4 would be 3 out of 6. But we have to subtract the overlap since we counted 2 in this group and this group. So that's why we're going to subtract 1 out of 6. So to find the probability, it's just the number of numbers over the total number of outcomes, which is 6. So 3 plus 3 is 6, and 6 minus 1 is 5. So that probability is going to be 5 over 6. All right, the second example says, what's the probability of drawing a jack or a diamond from a standard deck of cards? So jack or diamond. I like to write it out. So it's the probability of jack plus the probability of diamond minus the overlap. So the card that is a jack and a diamond. So in terms of how many jacks there are 4 jacks out of 52 total cards. In terms of how many diamonds there are 13 diamonds out of 52 cards. And then the overlap would be the card that is both a jack and a diamond. So that would just be the jack of diamonds, and there's only one jack of diamonds in a deck of cards. So that's 1 over 52. So when we add these together, 4 plus 13 is 17, and 17 minus 1 is 16. So that probability would be 16 out of 52. All right, next example, we have numbered cards from 1 to 20 and picked one at random. Probability that the card picked is a multiple of 2 and a multiple of 5. So multiples of 2 are 2, 4, 6, 8, 10, etc. Multiples of 5 would be 5, 10, 15, 20. So we're trying to find the probability that it's a multiple of 2 or multiple of 5. So let's first find the probability that it's a multiple of 2. So if we're numbered from 1 to 20, that's going to be 2, 4, 6, 8, 10, 12, 14, 16, 18, 20. So there are 10 multiples of 2 out of 20 total cards. Multiples of 5 would be 5, 10, 15, 20. So that's 4 out of 20. And then overlapping cards that are both multiples of 2 and a multiple of 5, that's going to be 10 and 20. So that's going to be 2 out of 20. So this should be a subtraction right here. So the reason we're subtracting 2 because we counted 10 in the first group and we counted 20 in the first group and we counted them in the second group as well. So since we counted them in both groups, that's why we're subtracting it. So 10 plus 4 is 14. 14 minus 2 is 12. So the probability would be 12 out of 20. All right, the next rule is the multiplication rule, and this is the probability of event A and event B is the product of the probability of A and the probability of B given that A has happened. So in symbols, this is what it looks like. The probability of A and B happening is the probability of A times the probability of B given that A has happened. If the two events are independent, we still multiply them, but the probability of finding B is going to be a little bit different than this one. So to kind of demonstrate the difference between these two, let's look at these two options. Or these two problems. So it says, what's the probability of getting 4 clubs when drawing cards out of a deck with replacement? So if we're getting 4 clubs, that essentially means I'm trying to draw a club and a club and a club and a club. Right, that's the same thing as saying 4 clubs in a row when drawing cards with replacement. So in this case, since we're trying to find and, we know that we're going to be multiplying. And since we're replacing the cards, that means this is considered an independent event. The probability of picking a club on the first draw in no way affects the probability of picking a second club. So for the first club, the probability of picking a club is going to be 13 out of 52. The second club is still going to be 13 out of 52. Third club is 13 out of 52, and for the fourth club, it's going to be 13 out of 52. So another way we could write this, since the probability is the same each time, would be 13 out of 52 to the 4th power. So that probability, 13 over 52 to the 4th power, is going to be 0.0039. So now let's look at the second one. So this is the case, this example when we're drawing with replacement is basically this example, okay? So for the second one, it says, what is the probability of getting 4 clubs when drawing cards out of deck without replacement? So since we're not putting the card back, that affects the probability on each draw. So we're still trying to find the probability of picking a club and a club and a club and a club. However, that probability is going to change on each draw. So on the first draw, it's going to be the same. It's still 13 out of 52. But on the second draw, this is where we're looking here. So it's the probability of A times the probability of B given that A happened. So the probability of picking a club given that we picked a club on the first draw. So if we picked a club on the first draw, that means there's only 12 clubs left. And since we didn't put the card back, that's 51. All right, so here's an example. We're still multiplying, but the only difference between these two is that probability on the second, the probability of the second event is going to be different than the first event because of what happened the first time, right? And then if we draw a third card, it's going to be the same thing. We're drawing a club given that we drew 2 clubs before, so that's 11 out of 50. And then lastly, on the last draw, it's going to be 10 out of 49. So that probability when we put it in our calculator is going to be 0.0026. So that probability is slightly lower when we're not replacing the cards. So this is this is an example of this particular rule here. Okay, regardless, you don't really have to think through if an event's independent or dependent. Just know that when you are multiplying the probability, or when you are finding the probability of 2 events happening, both of the events, meaning A and B, we multiply those probabilities. How you think about the second probability might be affected based off the first one, whether they're independent or dependent events. We can also use the multiplication rule when finding probabilities in using tree diagrams. So if we look at this example, it's talking about mammograms and talking about when a woman has a mammogram, sometimes you have a false positive or a false negative. A false positive would mean a woman who doesn't have breast cancer tests positive from the mammogram, and a false negative would be someone who does have breast cancer actually tests negative for based off the mammogram. So in this situation, it gives us a few facts. So it says 1% of women aged 40 or over in this region has breast cancer. And then it says for women who don't have breast cancer, or who have breast cancer, the probability of a negative mammogram is 0.03. For women who don't have breast cancer, the probability of a positive mammogram is 0.06. Make a tree diagram for the situation. So we're kind of dealing with two things. We're dealing with people either having breast cancer or not having breast cancer, and then whether they get a positive or negative mammogram. So the information given in this particular problem is that 1% of women aged 40 or over have breast cancer. So we have two situations. Someone either has breast cancer or they don't. And the probability of someone having breast cancer is that 1%. So that's 1%, which could be written as 0.01 as a decimal. That means 99% of women do not have breast cancer, which as a decimal is going to be 0.99. Then from here, a woman takes a mammogram. They either get a positive mammogram or a negative mammogram. And it says for women who have breast cancer, the probability of a positive mammogram is 0.06. Or sorry, women who have breast cancer, the probability of a negative mammogram is 0.03. So this probability right here is going to be 0.03. Which means the probability of having a positive mammogram would be 0.97, since those should add up to 100%. Then it also gives us that for women who don't have breast cancer, the probability of a positive mammogram is 0.06. So that's a false positive. Which means the probability of a negative mammogram in someone who doesn't have breast cancer is going to be 0.94. So then from here, we can answer some questions using this tree diagram. So it says, what's the probability that someone has breast cancer and that it's detected, meaning that they have a positive mammogram? So that would be breast cancer and that it's detected, which is 0.97. I'm sorry if you can hear my son banging things in the background. So in that case, we're going to do 0.01, which is the probability that someone has breast cancer, times the probability that they have a positive test, which is going to be 0.97. So that probability is going to be 0.0097. And actually, we can use that idea to find the probability of every outcome. So, for instance, the probability of someone having breast cancer and testing negative, we would multiply that. So 0.01 times 0.03 gives me 0.0003. And then going down to the second set of outcomes, no breast cancer testing positive, that would be 0.99 times 0.06, which is 0.0594. And then lastly, having no breast cancer and testing negative, which is the most common case since a lot of women do not have breast cancer, 0.99 times 0.94. That would be 0.9306. And as we saw that first probability rule or second probability rule, the sum of these probabilities should all add up to 1. So if we were to add these together, those should all add up to 1. All right, so then once we have those, now we can say, what is the probability of a positive mammogram? Well, we have a positive mammogram in this case and in this case. So the probability of having a positive mammogram, we would just add those together. So 0.0097 plus 0.0594, because we have to take into account that some women who are having mammograms have breast cancer and some do not. So 0.0097 plus 0.0594. That's going to be 0.0691. So if we looked at all of the mammograms that are taken by women in this region, approximately almost 7% of those would be positive. Some of them would be women who have breast cancer, and some would be women who do not have breast cancer. All right, let's look at some more multiplication rule examples. So this is proportion of right-handed pitchers in the MLB is 0.72, and the proportion of left-handed pitchers is 0.28. Assume it's impossible for a pitcher to be both left-handed and right-handed. Suppose you select two MLB pitchers at random. What's the probability that both are left-handed? So this is another application of the multiplication rule because we want to find the probability that the first person is left-handed and the second person is left-handed. So in this case, we're going to do 0.28 times 0.28, or 0.28 squared. And that's going to be 0.0784. All right, so now it says, suppose you select two MLB pitchers at random. What's the probability that one is right-handed and the other is left-handed? So what I should have done in the first situation is probably draw a tree diagram showing all the different outcomes of how you can pick two pitchers from the MLB. So for the first pitcher, we know the first pitcher can either be right-handed or left-handed. And then the second pitcher that we select can be right-handed or left-handed. Right, and then filling in these probabilities, we know the probability of being right-handed is 0.72. Probability of being left-handed is 0.28. So in the case that we just saw, the probability of choosing two pitchers and that they're both left-handed was 0.28 times 0.28. But now we can see clearly that if we want one pitcher to be right-handed, one pitcher to be left-handed, there's two different ways we could do that, right? We can have the first pitcher we select to be right-handed and the second pitcher we select to be left-handed. So that'd be 0.72 times 0.28. But we can also have the case where we have one left-handed, the first pitcher's left-handed, the second pitcher's right-handed. So that's also going to be 0.28 times 0.72. So we would have to add those two probabilities together. So 0.72 times 0.28 is 0.2016. So both of these 0.2016 and 0.2016. And since there's two different ways that we can select a right-handed and left-handed pitcher, it's double that probability. So that's going to be 0.4032. All right, so now that we're familiar with the at least one, or the multiplication rule, now we can apply that multiplication rule to what's called the at least one rule. So when something happens at least one, that's basically the complement of an event not happening. So the way you can think about it is the probability of the event not happening, or the probability of the event happening at least once, is equal to 1. So the probability that it doesn't happen plus the probability that it happens at least once is equal to 1. So based off of that, we can rewrite that as saying the probability that something happens at least one is 1 minus the probability that it doesn't happen at all. So let's take an example here. It says roll a single die 5 times. What's the probability of at least 1 6? So as soon as I see I'm trying to find the probability of at least 1 something, I'm going to rewrite it using this rule here. So probability of at least 1 6 is equal to 1 minus the probability of no 6s. Because either when you roll 5 dice, you're either going to get no 6s or you're going to get at least 1 6. So to find this probability, what we need to do is we need to calculate the probability of getting no 6s in 5 rolls. Well, we know that the probability of getting a 6 is equal to 1 out of 6, which means the probability of not getting a 6, that's just the complement rule, is going to be 5 out of 6. But since we're rolling the die 5 times, we want the probability that none of them are 6s. That's going to be 5 over 6 to the 5th power, because we want the first roll to be not a 6, the second, third, fourth, and fifth to be not a 6. So to find the probability of at least 1 6, we're just going to do 1 minus 5 over 6 to the 5th power. So again, this 5 over 6 to the 5th power represents the probability of not getting any 6s, and we're subtracting it from 1 because the probability that we're actually trying to calculate is getting at least 1 6. So when we put that in our calculator, it's going to be 1 minus 5 over 6 to the 5th power. Sorry, you are hearing all kinds of noises in this video. So that's going to be 0.5981. So probability of at least 1 6 is going to be 0.5981. Okay. So now let's look at the second one. It says the proportion of Americans who have type O blood is 6.22%. If 10 people appear at random to give blood, what's the probability that at least one of them has type O blood? So like I said, as soon as I see the at least one, I'm going to rewrite it as a probability of at least one type O negative blood is equal to 1 minus the probability that none have type O. And remember that the probability that we have to calculate is the probability of none. Well, the probability that they give us is the probability of someone having type O blood, which as a decimal is going to be 0.0622. So that means the probability of someone not having type O is 1 minus 0.622, or 0.0622. So 1 minus 0.0622 is 0.9378. And then since we're looking at 10 people, we know that the probability that none have type O blood is going to be the 0.9378 to the 10th power. So this probability of not having type O blood is going to be 1 minus 0.9378 to the 10th power. So this probability after the 1 represents a probability that none of them have type O blood. So putting that in our calculator is going to be 1 minus 0.9378 to the 10th power. So the probability that at least one has type O blood is going to be 0.4739. So final answer is going to be 0.4739. All right. So lastly, if 4 cards drawn from a standard deck of 52 cards are not replaced, find the probability of getting at least 1 heart among the 4 cards you select. So again, I'm going to rewrite this in terms of the rule. So the probability of at least 1 heart is 1 minus the probability that none of them are hearts. So let's figure out this probability. Again, we're figuring out the probability of none. So let's figure out the probability of a heart. That's 13 out of 52. Since there are 52 cards in a deck and 13 of them are hearts. So that means the probability that it's not a heart, using the complement rule the first time, is going to be 1 minus 13 out of 52, which is 39 out of 52. But since we're drawing 4 cards without replacement, the probability that none are hearts. So here's where we have to be careful because they're not being replaced. We know that this is the case where they're not independent. So we have to calculate the probability given that we drew a heart the first time, or not a heart the first time. So on the first draw, it's 39 out of 52. On the second draw, it's going to be 38 out of 51, then 37 out of 50, and then lastly 36 out of 49. It's a probability of none. We're still using the multiplication rule. So just like in the previous example, we were using the multiplication rule, but we can just raise it to a power since the probability was the same for each person. In this case, the probability is going to change because we're not replacing the heart. So in this case, this right here represents the probability that none of the cards that you draw are hearts. So it's this probability right here. So to find the probability of at least 1 heart, we're going to do 1 minus that. So I'm going to put that in my calculator. So the probability of at least 1 is going to be 0.6962. So this whole probability, I put it in my calculator, is 0.6962. Probability of at least 1 heart is 0.6962. All right, so the next concept, and actually the last concept, is conditional probability. So conditional probability of A given B looks like this. So this is what so we use conditional probability when we see the word given. This is what the formula is. So the probability of A given B, so that line stands for given, is the probability of A and B divided by the probability of B. So this is the idea, and we've actually already used conditional probability when we've done sampling with without replacement right here, right? So the probability of choosing a card that is not a heart, given that we chose a heart the first time, is this. So let's just look at this rule here. It says the probability of event A is 0.5. The probability of event B is 0.6. So then it says if the probability of both A and B is 0.1, what's the conditional probability of A given B? Well, using the rule that we see here, that's going to be the probability of A and B, which is 0.1, given that the probability of B, which is 0.6. So that's going to be 0.1 divided by 0.6 which is 0.17. So we can actually also show this in a Venn diagram if we wanted. So here we have A and here we have B. And we know the probability of A and B is going to be 0.1. So the probability event A is 0.5, which means that this is 0.4. So the whole thing is 0.5 in total. And then for B, it's 0.6, which means just B would be 0.5. So if we're trying to figure out the probability of A given B, we want to know the probability of A and B, which is going to be the 0.1, over the probability of B, which is 0.6. So this is essentially saying we know that we're looking at the probability of B. We want to know what proportion is just A, which is going to be the 0.1. That wasn't a very good explanation, so let's take a look at another example. Okay, so it says, in an apartment complex, 40% of residents read USA Today, only 25% read the New York Times, and 5% of residents read both papers. Okay, so let's make a Venn diagram of this situation. So we have USA Today, and we have the New York Times, and we know that 5% read both. Okay, so that means that if 40% read USA Today, that means we have 35% that just read USA Today. And then if we know that 25% read the New York Times, that we know that means 20% just read the New York Times. So in this particular case, we're looking at what is the probability that a randomly selected resident reads the New York Times given that they also read USA Today. So in this case, we're only looking at the circle on the left-hand side. We know that this person reads USA Today. That means our denominator is going to be 40% or 0.40. And of that percentage, the percentage that read the New York Times is just that 5%. So that's the New York Times. So that's going to be 0.05 on top. So on top is a probability that they read both. So that's a probability USA Today and the New York Times. And then the denominator is the given part, probability that they read the USA Today. So 0.05 divided by 0.40 is 0.125. So you can also use conditional probability when working with tables. So here we have what's called a two-way table, and it's called a two-way table because we have two different variables we're looking at. We're looking at a school, people who eat breakfast regularly and people who don't eat breakfast regularly. And then we're breaking that apart by males versus females. So in this school, there's 595 people who were in the school. We have the totals for people who eat breakfast and don't eat breakfast, and the same thing for male and female. So the first question says, if we select a student from the school at random, what's the probability that the student is a female? So female, the total is 275, so it's going to be 275 over 595. I'm just going to leave them as fractions. Next one is someone who eats breakfast regularly. So that total is going to be a row total. That's 300. So that's going to be 300 over 595. This one is a female and they eat breakfast regularly. So in this case, we're looking at the intersection of a column and a row. Female who eats breakfast regularly. So that's going to be 110 over 295. Or sorry, 110 over 595. All right, the next one, it says a female or eats breakfast regularly. Well, remember the or rule, we add and subtract the overlap. So in this case, it's going to be the probability that the student is female, so that's the 275, plus people who eat breakfast regularly, which is 300, minus the overlap. And in this case, the overlap is the 110. So that's going to be 465 over 595. So then now we're getting into conditional probability. It says someone who eats breakfast regularly given that the student is female. So in this case, that the student is female is going to go in the denominator. And that total is 275. And then we want to know, so we're only looking at this column right here. And in that column, the people who eat breakfast regularly, that's going to be 110. So that probability is going to be 110 over 275. And then the last question says, a female given that they eat breakfast regularly. So eat breakfast regularly, we're going to be looking at this row in the table. And so that total is going to be 300. And then in that row, the total number of females is going to be 110. So in this case, for E, the numerator, we're looking at people who are female and ate breakfast regularly over the given, which is female. And to contrast that with F, the numerator was still female and eating breakfast regularly, but the denominator was the people who eat breakfast regularly. So the difference in this case was the given information.